Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, minimum number of operations to make all the array elements equals to 1. In this particular video, we will be looking at couple of different follow-ups as well, which is harder than the current version of the problem. I would encourage you to stay till the end, I will link all the timestamp in the description down below so that you can, if you are interested in just the follow-up, you can directly jump to that part instead of watching the entire video. So with that, let's get started. The problem states that you are given a zero indexed array nums, which consists of positive integers, and you can apply this following operations any number of times. The operation is you will choose an index I such that both I and I plus 1 exists, and you will replace nums of I or nums of I plus 1 with their GCD. Now you need to return the minimum number of operations such to make the entire array equals to 1. If it is impossible to make every element equals to 1, you will return -1. So let's take an example. Let's say this is the array 2634 and we selected I as this particular index. So basically what we are saying that we are free to replace either this 3 or this 4 with the GCD of 3 and 4. Now GCD of 3 and 4 is 1, so you can either replace 3 with 1 or you can replace 4 with 1. So let's say we decided to replace this 3 with 1. So the final array is now 2614. Now let's say we choose this 6 as the index I. Now what this means, it means again we can replace 6 or 1 with their GCD. So GCD of 6 and 1 is 1. So you can replace either 6 with 1 or you can replace 1 with 1. So let's say we decide to replace this 6 with 1. Again, let's say we took this particular index I. We can replace this 2 with GCD of 2 and 1, which is 1. And finally, we take this pair, another number of time, another one, and replace this 4 with GCD of 1 and 4, which is 1. Right? Now, in just 4 operations, we are able to convert this array into a array which has everything equals to 1. You can try any other possible combinations. You will not be able to convert the entire array into 1111 in less than 4 operations, and hence the result here is 4. Now let's take one more example. Let's say 2, 10, 6, 14 is the array. In this case, even if you do the GCD of entire thing, basically the problem states that you can do GCD of adjacent ones in one operation. So in best case, what you can do is you can take, like, you have to take GCD of 2 and 3, let's say. So what you can say is you will take the GCD of entire 2, 6 and 3, so that you will get the contribution of 3 in this 2 as well. So in best case, what you can do, you can simply take the GCD of entire thing and you can replace every number with that. But even if you do that, the GCD of entire array here is 2. And because GCD of entire array is not equals to 1, there is no possible way in which you will be able to replace any of this element with 1. And hence the answer here is -1. So hope the problem statement is clear. Now how to solve this? We already understand what the -1 scenarios correctly. Like if GCD is not equals to 1, we will simply return -1. Now let's look at the solution where their GCD is actually equals to 1. So this is one of the array which has the GCD equals to 1. Now how to solve this? So let's say you decided to perform one operation on this index, on this 42, and replace this 42 and 16 with the GCD which is equals to 2. Now the updated array is 2, 16, 18, 30, 25 and 15. Now what you want with this updated array? With this updated array as well, you want the same thing. What is the minimum number of operations in which I can make entire array equals to 1? Isn't this problem exactly same as the original problem? Original problem says that figure out the minimum number of operations required to make this array equals to 1, and like make all the elements here equals to 1. And the reduced problem is figure out the number of moves required to make this updated array equals to everything here is equals to 1. So hope you can see the recursion here. The simple recursive formula would look something like this. We will iterate, like the input will be an array, right? And we will try every possible combination. Now here I have just taken one side of the thing, like I am always replacing nums of I, right? but it can happen that you will replace nums of I plus 1 as well. So basically there will be another for loop after this, but I'm not showing this because that doesn't matter much in terms of complexity. So in this case, you will prepare the new array and just call the same function for the new array and just do plus 1 because you have just now done one operation. And you can do this, and finally the result, you will be having the minimum number of operations that is possible. Now, what is the time complexity? Now, forget about what we are doing inside. Let's just figure out how many distinct ways this function can be called, right? So, what can happen in one step? In one step, the best thing that can happen is, let's say this number has 10 factors, right? Now, the best thing that can happen is it will reduce one of its factor. Like, this is the best thing that can happen in just one operation, right? So basically, any value can take 10 distinct values in worst case. So the number of different possible arrays is 10 to the power 50, right? Why 50? Because the size of the array is 50. So each element can take 10 distinct values, and each of these elements are independent. So 10 into 10 into 10 into 10 up to 50 times, so 10 to the power 50. Now surely this will not pass, and we have to optimize this. Now how to optimize this is the next section. So whenever you are given these kind of problems wherein you are given some kind of transition, right? So there are two possible ways to optimize. Either you can convert this entire problem into a graph problem, and you will say that, okay, I will apply shortest path algorithm to figure out the required result. Or I will do some observation and prove that the observation is correct and then figure out the answer. So second approach, like doing observations and then figuring out the proof of the observation, is always very hard. So always try to first model this in terms of graph. If that doesn't apply, then only go with the second one. In this case, just to give you an idea, this will not be applied. Why? Let's look at it. So shortest path you can apply when the given graph at hand is static graph, right? If it is a dynamic graph, like if it is changing frequently based on some other factors, you can't apply shortest path or Dijkstra there. So in this case, the graph would be dynamic. What I mean by that, let's say for 42, you can take 42 to 2, which is the GCD of 42 and 16. Now from 16, you can transition to 2 again, because for the GCD of 42 and 16 is 2, and GCD of 16 and 18 is also 2. So basically you can only transition to 2 from 16. From 18, you can transition to 2 because GCD of 16 and 18 is 2, or you can transition to 3 as well because sorry, not 3, 6, because GCD of 18 and 6 is 18 and 30 is 6. Now from 30 again you will transition to 6, or you can transition to 5, right? Now notice that from 2 where will you go? It all depends on what will be the value after you have converted this, let's say 42 to 2. So what is the value after this? Based on that you will decide whether to go, like where to go from 2. So let's take one concrete example. Let's say 6. So 6 has three choices: either it can go to 2, or it can go to 3, or it can go to directly 1, right? Now which of these choices will you take, or which of these path is valid? This path will be valid if you will have some value, like if 18 is converted to 2 or 25 is converted to 2 somehow, right? Otherwise this path is not valid. Same goes with this path. So basically the graph is dynamic, it depends on external factors, and hence you can't solve it via shortest path algorithms. So now only thing that is left with us is we have to make some observation and then figure out and then somehow prove that the observation is correct and then solve the problem. Now how to solve this? Like again, one simple thing can be, let's say there is one in the array already, right? So what would happen if there is already one in the array? I would strongly encourage you to pause the video and try to think how many steps are required to make everything equals to 1 if there is at least one 1 in the given array. So in this case, the number of operations required would be equals to n minus 1, or particularly the number of non-ones in the array. Now, why this is true? Like we can, like with n minus 1, what we're saying is every element can be made to 1 in just one step. Now, to make this 30 to 1, you have to make or you have to take GCD of 30 and 1, because 30 and 1 GCD will be 1, right? So but you're not allowed to take GCD across like non-adjacent elements. So what you will do, you will simply say that, okay, I will first convert this 15 to 1. So whenever I have to take GCD of 30 with some other element which is not adjacent, I will just take the GCD of everything in between, and that will give me the contribution of every element to 30, right? So in this case, what we can say, we'll convert 15 to the GCD of 15 and 1, which is 1, right? And then we will convert this 25 to the GCD of 25 and the GCD value here, which is 25 and 1, which is 1, right? And finally, we can convert this 30 to the GCD of 30 and 1, which is 1. So this 1 contains the GCD of every element here, right? So if you just take the GCD of 30 with this one, you will get the contribution of every element in this range, right? So basically, we are able to propagate this one all the way to every other element in just one step. Basically, in one step, we are propagating to one element, and uh, as soon as an element gets it adjacent in one, we can convert this element to one as well. So number of operations required here is the number of non-ones element in the array. Now, what about the case where there is no one in the array at all? So you can argue that, okay, simple, right? Let's try to convert any of these element to one. Let's say we convert 30 to 1, right? Now, which element to convert is something which is different. We'll come to that. But let's say we convert any of these elements to 1. Now, once we have converted any of the element to 1, we can simply apply the same trick. We can say, okay, because this element, there is one in the array already, the number of operations required would be the number of non-one elements in the array, right? Now, how will you convert a number to 1 is the problem, and which one to convert is actually matters, and we'll come to that. But for now, let's try to focus on how to convert a particular index value to 1. So you can see that 30 has three factors, right? 2, 3, and 5. So to convert 30 to 1, you need some element which have which have which doesn't have 2 as a factor, which doesn't have 3 as a factor, and which doesn't have 5 as a factor. Then only you will be getting 1 when you take GCD of 30 with that number, right? So for now, let's assume that this is 75 for a good example, and 75 also has one more factor, which is 3. Now, which elements are required to make 30 equals to 1? So we required one element which doesn't have 2. So what is that element? Either 75 or 15. Now, which one of these two will you choose? You will always choose the closest one, because we have seen that to get the contribution of any element, we have to go via every element which are non-adjacent as well. So if you pick 15 here, then to merge 15 with 30, you have to first merge 15 with 75, and then you will merge 75 with 30. So you have to go via that. So always better to choose the smallest one first. So now we have to choose an element which doesn't have 3 as a factor. Which is this element? 16 is the only element which doesn't have 3 as a factor. Now you have to merge this 60, or in other words, you have to take the GCD of 16 with 30 somehow. And how you will take that? We have discussed that. Basically, we will take GCD of 16 and 18 first, and whatever is the result, we will take the GCD of that result with 30. and that will ensure that we are getting the contribution of 16 to 30 as well, right? Now finally we have to find one element which doesn't have 5 as a factor. So again, there are like 18 doesn't have 5 and 16 also is the one which doesn't have 5, so any of these two will work. Now what we want is we want to find out the smallest range in which we can make our job done. So we have seen that 15 is an element which doesn't have 2, but we have skipped 15 because 75 is more closer to 30. So we have to pick the smallest range in which if we do the GCD everything is equals to 1, then only we can make this 30 to 1, right? So just to reiterate, what we want to convert this 30 to 1, and to make that happen we have to find some numbers which doesn't have the factors which are contained in 30. So we have to, there can be multiple possible numbers that satisfy these conditions, but among all such combinations we have to take the smallest range in which this condition is satisfied. So this is the smallest range in which the current condition that is satisfied. So we will say that okay, whatever is the length of this range, that many number of operations will be required to make 30 to 1. Now why that many operations? As we have discussed, we have to we have to take the contribution of 16 to 30. So for that you need to first do the GCD of 16 and 30, and then you will do the GCD of 18 and 30. So finally you will get the contribution of everything in the left, right? And to gain the contribution 75 you have to do another operation. So basically you are doing exact number of operations as many like you are doing as many number of operations as many elements that you have considered, right? So what we want finally is we want to figure out the smallest range L to R such that the GCD of every element is like GCD of the entire range is equals to 1. Now this L2R must contain I as well, right? So that's the problem, or that's the algorithm. Basically, for if you want to find out how many operations or how many minimum number of operations are required to make an array element equals to 1, you will figure out the smallest range which GCD of which is equals to 1, and that contains I as well. And that range will give you the smallest number of operations required to make the element at index I equals to 1. So the pseudo code for that would look something like this, right? So initially you will initialize your result with n because in worst case you have to take like L would be the first element and R would be the last element. So you have to take every element into consideration to convert a particular element to 1, right? So after that, you will try every possible L and R. Now, what are the possible values of L? Possible values of L are this, right? Because you have to consider I in every scenario. So these are the possible values of L, and possible values of R are this, right? So you have to consider I in every scenario. Now you will do the GCD of every element from L to R. Now if GCD is equals to 1, then you will just take the minimum of the range uh, which you have like which is containing this LNR, right? And this will give you the minimum number of operations that is required to convert an element, the value of an element to equals to 1. Now what you can do is you can simply figure out this minimum steps required for each of the array elements here, right? And you will figure out minimum number of steps required for 42, minimum number of steps required of 16, 18, 30, 75, and 15. And then whichever takes the minimum steps, that one you will convert to 1. Basically, if you remember, our motive was to convert any of these elements to 1. Basically, we want at least one 1 in this array. So we have to convert any of this element to 1. And for that what we are saying is we will convert the one which requires minimum number of operations. So we already know how many operations are required for converting the 30 to 1 with this function. Similarly, we know how many operations are required to convert this 15 to 1, and so on and so forth. We'll take the one which require minimum number of operations. Let's say in this case, let's say 16 requires minimum number of operations, just an example, and let's say minimum number of operations is 6. Now the final answer would be x plus the n minus 1, right? Now why this is the case? Because we know there is only one 1 in the array, and that 1 comes because you have done x operation. After that, this element will be 1, and every other element will not be 1, and you will just take the, like, you will just propagate this 1 to every other element in n minus 1 step. Now some of you might be thinking that, okay, we require x number of steps to make this to 1. Let's say we require, like we have seen that for 30 we require 3 steps. So in these 3 steps we have also done some operations, right? We have done GCD of 16 and 18 and replaced 18 with that GCD value. Similarly, we have done GCD of 75 and 30 and replaced this 30 with this value, right? So what if doing this GCD can get me 1, right? So what we are saying is, after this element will be equals to 1, all other element will be not 1, and that's why we are saying that the answer would be x plus n minus 1. Like x, because we have to x comes because of the first element that we are converting to 1, and n minus 1 because we are assuming that all other elements will not be equals to 1. Now we have to prove this case as well, that even after applying this operation, x number of operations, all other elements will not be equals to 1. If we are able to prove that, then we can say that, okay, this formula works, or this observation works, that if we can convert one element to 1, and then we can just propagate that 1 to every other element in n minus 1 step. Now the thing to prove is that in the journey of making a particular number to 1, we are not making any other numbers to 1, right? So basically we have taken 16 and 18 GCD and replaced 18 with that value. Now what if this value, we have to prove that this value can never be equals to 1, right? So how to prove this? Again, let's say this value is equals to 1, right? Now if this value is equals to 1, it means that the number of operations required to convert 18 to 1 is smaller than number of operations required to convert 30 to 1. And if that's the case, we will be converting 18 instead of 30, right? Basically, if you get 1 in between, it means that like number of operations required to convert that number to 1 is smaller than the number of operations required to convert a number after that number, because you are propagating everything right so that you can make this number to 1, and you have said that this is the smallest, like this is the number which requires smallest number of operations. So that contradicts, right? Basically we are saying that 30 is the number which requires smallest number of operations. Now we are saying that 18, like in the journey to make 30 to 1, 18 already become 1. So in this case, it means that 18 has less number of operations, which is not the case, because 30 has greater, like 30, we already have picked 30 because 30 is the one which have the smallest number of operations, right? So this is the proof standard method to prove by contradiction. If you didn't understand this, I will encourage you to watch the previous 5 minutes of the video, and you will get this particular part. So now we have proved that if we choose the one which have the minimum number of operations, all other elements will never be equals to 1, and hence we can simply do x plus n minus 1, and that will be our answer, right? So what is the algorithm? We will first figure out the smallest number of operations for each of these indexes by calling this function, and then for we will pick the one which have the smallest number of steps required, and the answer would be x plus n minus 1, right? So what is the time complexity? We are calling this function n number of times for each of the index. And this function complexity itself is order n cube log n, because there are two loops, and inside this loop there is another loop to calculate GCD. So GCD of two numbers takes log n time, and we are doing this n number of times in the worst case. So this entire thing would take n log n, and this n log n exists inside this loop, which is of order n square time. So this function itself is order n cube log n, and we are calling this function n number of times. So this the complexity would be n to the power 4 log n, and this would pass because n here is very small, right? We'll look at the follow up to reduce this, but for now this will pass because n here is very small. Let's look at the code. Again, strongly encourage you to pause the video and try to code this solution yourself, because this just include this function and nothing else. So the code is very straightforward. We first calculated out the GCD of the entire array. If GCD of entire array is not 1, we'll return -1. Otherwise, we figure out if there is already a 1 in the array. If there is a 1 in the array, we will return, we can use that 1 to propagate to other numbers, and the number of operations required would be the number of non-ones in the array, right? Finally, if that's not the case, we will figure out the steps to 1 for each of the indexes. So we will simply do the exact same algorithm that we have discussed. We'll go over all possible L and R and figure out if which of these L and R range is valid, and take the one which have the uh, minimum range. And finally, once we get the steps to 1 for each of the indexes, we figure out the minimum among all of these. And this is the one, like this element is the one which we will convert to 1, and every other element will not be equals to 1 during this process, because we have just proved that, right? So the number of operations required would be that plus n minus 1, right? So hope this entire solution makes sense. If you have any doubts in this particular uh, solution, feel free to post them in the comment section below. Now comes the interesting part. We have solved this in order n to the power 4 log n. Let's see how to solve this in order n cube log n first, right? So notice that where from this power 4 log n comes. N cube log n was the complexity of this function itself, right? And we are calling this function n number of times, and that's where uh, we got n power 4 log n. So if we have to reduce one n from here, you have to reduce this n from this function itself, because we can't afford I like calling this function once. We have to call this function once for every index for sure. So we have to reduce the complexity of this function to order n square log n. Now I would encourage you to pause the video and try to think this yourself first. Now uh, see that this GCD is the innermost for loop, which iterates over everything in L and R and figure out the GCD. So GCD of a range L and R can be found easily with the help of segment trees. So this itself you can find in order log n time, right? And hence the complexity of this entire function would reduce to order n square log n, and the overall complexity would be n cube log n. Now, if you don't know about segment tree, I already have started a series of segment tree and we have started that series from scratch. Like I have discussed the basic segment tree from scratch in one of the videos, and then we have like a couple of videos in which we have solved various different problems of segment trees. So I would link that playlist in the description down below. Make sure to check it out if you don't know segment trees, or if you want to strengthen your understanding of segment trees. Now we have reduced this to order n cube log n. Now, can we reduce this further to n square log n? Answer is yes. How? Again, the same thing. We have to remove this n square completely from here. So basically, we can't afford calling this function one time. We have to call this function n number of times. So n will be there. So we have to ensure that this function itself runs in order log n time. So we already have removed one loop from here, right? So to make it n log n, we have to remove another loop. So basically, we are saying that r should also be removed. So in other words, what we are saying that for a particular L, figure out what is the best possible R, or what is the closest possible R, right? And this as well, you can figure out using binary search and segmentary, right? So again, in the series, the next type of problem that we will be discussing is binary search, and I've already linked this particular problem in that. I would be uploading this somewhere in the next week. So basically, we can simply do a binary search over R and figure out what R is. I have already uploaded a binary search video also from scratch. I would link that as well. Make sure to check it out. We can simply do binary search for R and get the value of R, and this G will be calculated from GCD again. So like with just doing binary search, you will be getting a complexity of order n square log square n, but with a small modification of segmentary, this log another log value can be removed as well. So which we'll discuss further in the segmentary series. So that's it for today. If you have any doubts in any of the problems that we have discussed, feel free to post them in the comment below. If you like the video, give it a thumbs up and do subscribe if you're not already. And I will see you in the next one. Thank you.